Hello, everyone. My name is Amy, and I'm here to give an update on PyDSL on behalf of my colleagues, James, Ritsuka, Kevin, and Fabian. So background, PyDSL is a Python-based DSL that generates MLIR. It achieves so via the add-compile decorator, where it grabs out the Python AST for the function f, and it passes the AST along with the Python context structure to the PyDSL compile method. The compile method walks the AST and generates the corresponding MLIR, and further, it lowers the MLIR into an object file. The object file can be executed by passing NumPy arrays as inputs to it. Currently, we support CPU and Huawei's NPU Ascend target. We introduced a new feature, just like the C++ template for kernel specialization. A template decorator is introduced for this purpose. So add template works slightly different than the add compile decorator that was on the previous slide, in that it only grabs out the AST. For example, for the calc function, the compile is deferred to the invocation time of calc. So the AST is passed to PyDSL's compile method along with the concrete template parameters, in this example, F32, 10, and 5, injected into the context structure, and then passed to the compile method to generate the specialized MLIR. We also introduced a new autotune feature with the add autotune decorator. It works very similar to the add template decorator in that it injects the configuration parameters into the same context structure, and then it invokes the PyDSL compile method to generate the specialized MLIR and lowers that into an object file, and then run and then measure time. As it exhaustively creates the whole Cartesian product of all the configurations, this can be time-consuming, so only recommended for auto-tuning a small configuration space. We also introduced Triton interoperability support. This allows PyDSL to call an add Triton JIT method from a PyDSL method. This is achieved by looking at the call site, which is the PyDSL method, in order to figure out the type signature and the const expressions for the Triton method. It then grabs the Triton AST and invokes the Triton.compile to generate the TTIR. There is a typo there, it's the TTIR, not TTGIR. Anyway, it then invokes the Triton to linalg converter, the adapter, to convert the Triton IR into the upstream MLIR linalg dialect format. And it concatenates the Triton MLIR into PyDSL's main module, and then the whole PyDSL code is lowered. We also introduced some improvements, niceties to PyDSL this past year. For example, memref tensor indexing, notably with Python slicing syntax to implement memref subview, tensor extract slice, tensor insert slice. And we also support memref with strided layout for backends that have layout requirements. And we also support powerful reduce op that can do reduction along multiple dimensions with a custom combiner function. Last but not least, since last year, we introduced call macros. We have used call macros extensively in our support for NPU target. So the call macro is really a macro expansion of a Python AST into MLIR, so we call that a call macro, and it's meant for an extensibility feature for PyDSL. Last but not least, the whole PyDSL project have transitioned to an open source development model. We have built integrated robust CI for active development. So when you submit a PR, you can actually run the CI to see that it's green. All the issues are tracked in open source and the pull request. And we also have a Discord group with a QR code there to welcome everyone who wishes to join PyDSL development. And with that, that's the end. Thank you.